Mic check. Mic check 011001. Are we all here? Mic check. How are we doing? I'm just checking that it actually is working. Can anyone actually hear what I'm saying? I'm just checking chat to make sure. Savesh, yes. We don't mic check 1, 2 because there's no 2. There's only 0, 1. Also, DJ Chicken is in the house as per usual. There you are, DJ Chicken. Mic check 1, 0. We're learning about C, and as you can see, C's not always easy, but it's okay. Stick with me. Because even if you're overseas, we're still at CSE, Programming Efficiency, efficiently learning about C. 1, 2, 1, 2. All right. How are we all doing? That's my new rap for today. All right, let's go to the actual lecture. Let's see what we're up to today. Someone says they have an iron deficiency. I was trying to figure out all the different ways that I could rhyme C. I think it would be interesting. They're all very, very, very obscure. But see if people can figure out where I've stolen the raps from. Because the last 2 raps, one of them was from a song that I looked up last night that was released 20 years ago, so it's pretty obscure. And the one from today, all the raps on the word C, many of them were stolen from another rapper from the same era. I think it would be about 2001, 2002. Yeah. Anyway, there we go. Let's launch into the lecture, hey? So, what were we looking at last time? Last time we spent a bit of time thinking about writing code for humans. And I don't just mean writing code for other humans. I mean also writing code for ourselves as a human. Let me just, adjust my camera a little. It looked a little lopsided. I'm just going to make sure this is nice and level. Aiming at me. Yeah, there we go. So a lot of stuff about writing code for humans, and I showed you one example just to have a fun time with something that had nearly every code style mistake that's ever existed all boiled into one single program. But I think what was more important than that was going through a few things that you can think about that will help your code be more readable and also be more usable. So it's not just readable for other humans, we're talking about readability for the human that wrote it as well. So when we're writing code for ourselves, we're thinking about what happens in the future with our code. So I write my code and I'm working on an assignment, say, and I work on this assignment over the course of, say, I don't know, depending on how much time you spend on the assignment. Let's say I spend 8 to 10 days on the assignment in total. So the code that I wrote on the first day, by the time I get to the 8th or 10th day that I'm working on it, I may have completely forgotten what that code was because I've worked on all this other code in between. Maybe I worked on a lab in between which had other content in it as well. So I'm kind of all over the shop by then, and I'm relying on past me to have written that code well enough that future me can look at it and say, yeah, I get you. I get where you're going with that, and I still understand what that means because I can read back over it and understand it. So us planning for ourselves in that way is always a good idea. And even when we think about present me in the middle who's working on the code at the time, present me is often looking for why bits of the code isn't working, trying to find errors in the code, trying to figure out which bits are causing the program to not run the way that it's supposed to. And having really, really clear readable code makes it much easier to say, I can see that that bit is working. I'll look somewhere else for the error, that kind of thing. At some point, I think it might be next week, it's either next week or the week after, I will talk about techniques that we use for trying to pinpoint specific errors in our code and how to think about different types of errors and how to approach removing those errors from the code. I can't remember where I had a plan. I'm pretty sure it's next week because we're throwing you into an assignment at the end of this week. So we're planning on the release around Sunday, for this that will go for 3 weeks, and it will be tying together the content from the course. I would say the first 4 weeks of content from the course. So when we release it at the end of week 3, there may be some things in it that you're not 100% on, because we haven't had labs on it and some stuff that's still going to be covered in lectures. So if you want to start it immediately, there'll be bits of it you can definitely do, but otherwise there's going to be bits we're going to teach you about as we go along. Tom's working on it right now, so Tom's putting a lot of the finishing touches on the assignment, and then we'll be doing some testing with it this week before it goes to you over the weekend. What was I going to say about that? I distracted myself by reading the comments. That's okay. I'm sure if there's anything that I do need to say, I'll remember it as we go along. So we also introduced functions, but and I know because I stayed back afterwards with a couple of people to talk about them. All I did with functions last lecture was just deliver the theory of them. I showed some code examples, but I didn't actually write up the code to show you exactly how it's working or anything like that. So today we're going to do an example, and we're going to add functions into that as well. Having said that, today we are also going to be learning about something new, and that is going to be, I'll just jump to the second point here, talking about arrays, which is talking about oh, that's what I was going to say. Let me just finish this point. So, talking about using multiple variables at once in a collection where we know all the variables are related to each other in some way. So, we're going to start building up our use of computer memory into blocks of memory, not just a single item at a time. And I wanted to do a little bit of a discussion about the theory of the computer, in a sense. It's not even the theory, it's the practicality of the computer as well. It's how it's built. And so we're going to be talking about a bit about what a computer is, because I've given you the vague basics of there's a thinking bit and a remembering bit, and combining those two together gives us the capability to do modern computation. So we're going to look at some of the physical, well, not physical, I guess everything's physical on the computer, but some of the closer nitty-gritty of how it is and how we use it and how the theory relates to the practice. And so Gira-chan, you're asking about the structure of the assignment. I'm going to do a live stream sometime next week after the assignment is released. So I'll give people a few days to read the assignment, and then I'll do the live stream. I'm thinking at the moment that Thursday is a pretty good day for it, so I may do it either during the lecture time slot on Thursday or later in the day. I'll have a look at when the labs are and stuff like that, so I'll try to go in between 2 tute labs so people can come to part of it. But we'll talk about it then when you've got both something to read about and something for me to explain while you've got your reference there. But the assignment is kind of structured in a sort of an escalating difficulty thing. So the labs are sort of structured in escalating difficulty. The weekly tests are also sort of structured in escalating difficulty, that the earlier questions are easier than the harder questions. But the assignment's much more structured than that, because if we want to do something much bigger, we need to organize it. But I won't talk about it now, because I don't think it's worth talking about it without giving you the actual documentation where you can refer to it while I'm talking about it. But we'll definitely have this conversation, but it'll happen next week. Okay, so today, looking at how computers work on a theoretical and practical level, and then we're going to look at a slightly deeper use of memory than we've had before in arrays. So, question. I think I've asked this exact question before and talked about it a bit. What is a computer? And last time I talked about this, I was being very, very conceptual, talking about computers as tools, configurable tools that can do things. And today we're going to talk about, at the fundamental level of a computer, what are the bits that actually work in the computer, and what are the bits that we're worried about when we're thinking about how to control a computer and how to get a computer to carry out specific tasks. So at the deepest sort of level, if we think about only the fundamental parts of what the computer are, as I was saying before, the thinking part, the processor that executes instructions, that's a physical piece of the computer, there is something called the CPU, Central Processing Unit. You'll see computers being sold based on the brand name and the current specs of the CPU. I think the Intel i7 is still this kind of the de facto standard that most computers have nowadays. But then we also think about memory that holds some information. And I'm talking not just about the bit that people call memory, which is the random access memory, which is part of the memory structure of the computer, but just everything that stores data on the computer. And we'll talk about how we break that down. I've got some slides that go deeper into that. Um, yeah, Trent was saying AMD. What's it called? Is it the Ryzen? The AMD processor? I don't know that much about them because I haven't. It's like once every say 3 years or so, I get really knowledgeable about how computers are going, and then I buy one, and then I don't bother looking at it for the next few years. I used to professionally, because I used to spec computers for people to do things, so I used to professionally know what was the best processor, and it was like it's so much work. It's like a full-time job just to keep up with all of the updates on what people are building, and it's like at this point in the development cycle you should buy this one but not this one because this one just got cheaper and it's like middle of the road but it's now much more economic than this one. It's just it's so silly. So it's really hard to keep track of those things. Anyway, let's think about this in a theoretical way. So I introduced you to Alan Turing in week 1. So Alan Turing was he lived through World War II, and he was instrumental in Britain's efforts to create viable computing, in a sense. And he was able to create viable computing, and we think of him as people often call him the father of modern computing. So he came up with the idea of the Turing machine, and I said before that the Turing machine, the way that it models the idea of computation. One of the interesting things about it is that there's nothing that our current computers can do in terms of what they can mathematically possibly calculate that the Turing machine can't do. It just does it slower if you think about trying to do it by hand or anything like that. But there's nothing that it's theoretically capable of. There's nothing that our current computers can do that the Turing machine isn't theoretically also capable of, which is really full on when it's this simple. It's only 5 dot points on this slide. So we have this idea of a tape. So old school, right? It's just a piece of paper that's really long. So they used to call those tape because that's what they use. They use it in reels and stuff like that. And you can think about like magnetic tape also as being an option there, which is something we still don't use that much nowadays. I think maybe some long-term backup storage for companies is still tape, but I think a lot of it is all hard drive based nowadays anyway. But anyway, you can think of it as a long bit of paper that you can write stuff on. And there's a head, and the head, when you're using magnetic tape, is something that moves back and forth along the tape, or the tape moves along and it reads or writes to it. So the head can move along anywhere on the tape, read or write to it. And in that head part, there is a state where it remembers what it's up to at the current point in time, and it also knows what instructions to do. So it knows that based on the current state that it sees and what it's reading on the tape, it will decide what to do. So I've got a couple of images here of these that I took from Wikipedia. So there's some idea of control in the head that can move it back and forth. So this is like this motor here that can move the tape. And then there's like in the head, there's this idea that there's a possible eraser, there's an electric eye, like a camera looking at what square they're looking at, things, and this printer that can print ones or zeros on this tape. So this is like a mechanical version, but my favorite is this little version here, which is there's a person inside a box. So they can't see anything except for the ground below them, and they can move the box backwards and forwards along this tape. And inside the box, they can write stuff on the inside of the wall in the box, which is like what their instructions are, and what the current idea of their state is. And then they've got a bit of chalk and a duster. So with the chalk and the duster, they can they can dust off the ground beneath them, so erasing the number beneath them, and then they can chalk a 1 or 0 beneath them. And this little person in the box that just goes back and forth like that, given enough time, can compute anything that we can compute on a computer. So it has the same theoretical capabilities as a computer. Because when you think about it, everything that we're doing in C is either deciding what to do next or changing a value that exists somewhere. There's really nothing else that we're capable of doing. And when it boils down to the simplest level, this is all it is. It's just looking at what you think of the world right now and what you see of the world right now, and you can walk back and forth so you can see lots of things. So for example, if I wanted to see, say, an integer, I would take 32 steps along this thing and read all of these zeros and ones, and I would have some idea about what these zeros and ones mean. So written on the inside of my box, I would say, okay, if you get this kind of sequence of zeros and ones, it means do something, or it means it has this value, that kind of thing. So it gets awkward when you think about like feasibility of how much stuff you could actually write on the inside of a cardboard box that you could carry around. But theoretically, it still has the same capabilities. So when we think about how this works in our actual computers, so we have the CPU. It's a piece of silicon about yay large with a whole bunch of very, very hard to make and high end to the point of nanoscale technology in it. They're getting pretty close to what we'd call nanoscale technology, of a whole bunch of switches and a whole bunch of actually mechanical things that are able to process information. But all they're really doing is maintaining the state and being able to make decisions on what goes back and forth. A lot of the complicated stuff in processors is just to make those repetitive individual simple tasks easier by doing a dedicated piece of a processor to do it. So as much as they're super, super complex, all they really do is have the capability to crunch numbers. This CPU will maintain its own state, so it will know where we're up to in the code. It has enough capability within itself to remember where it's up to. It will know what instructions are, and it can then access the memory and read and write to it. So when you think about it, the CPU at a theoretical level is very much the same as that person in the box. There's not much else it's doing. If that person in the box was magically able to do several trillion, quadrillion calculations per second, then it could go as fast as the CPU and do the same things the CPU is doing. Let's relate that to our C programming. So our C programming has the same concepts because we're working in the same system, in the same environment, right? So the state that we're at, the maintaining of the where are we at right now, is actually which line we're up to in the code. So you think about it as when we move down our code line by line, when we hit a certain line, we have a memory of what's happened before. So that memory of what happened before knows which variables have been declared, knows which functions already exist, might know where we are in terms of, are we inside an if statement right now, and when would we jump out of that if statement? Are we inside a loop right now? Where do we jump back to when we finish that loop? All that kind of information is our state. And then we have our instructions. Our instructions is our entire code file, knowing that there's always going to be a next instruction after the one we're at, either that or the program finishes. And we know what to do when we see certain things. Like when we see a variable name or another function name or anything like that, we know what to see. And then this reading or writing to and from memory, we've already seen a bit of that, right? So I've been really kind of explicit when I'm talking about variables to say it's a chunk of memory. So it's some switches, these little switches inside your computer with ones and zeros that can be set. Those are how we save our variables. So in C programming, we've already been doing everything that the Turing machine can do. We've been maintaining a state by keeping ourselves up to date on where we are. So knowing that our code runs line by line, we've been writing the instructions ourselves, and the variables are how we keep information. So all of that kind of stuff is the stuff that we've been learning about already. Jaws is saying, poor dude. Yeah, that little person in the box is doing a lot of working. Okay, so let's look at memory, and I wanted to talk a little bit about how memory is actually set up on a computer. Yes, someone noticed that Chicken was there, so She walked off for a second there, but she came back because she had to remember that the lap is the best spot, and she just wanted to come back to it. I think I got a bit too animated with what I was saying a second ago, and she jumped off, but now she's back. So, when I talk about memory, I'm sort of expanding the idea from like commercially what we think of as memory to what I think of as everything in a computer that stores information. So there's all these other bits in the computer that aren't, in marketing terms, thought of as memory, yet they are all used to store the same kind of data that memory is. So we go from this scale of things that respond very quickly, but are very, very expensive to make at a large scale. So we don't have that much information in these, to things that are much cheaper to have lots and lots of information, but they're slower. And usually the slower, larger things are more permanent. So for example, your hard drives in your computers, they don't require power to remember information. And you might think, why would something need power to remember information? But everything beyond the hard drives, once you go into these other forms of storing information, they're much more volatile. So they don't keep information if you don't have electricity running through them. The trick is, the difference between these things is thousands of times difference in speed. So if I want to get information out of RAM, which is the kind of memory that you usually solder a computer on. So for example, my computer here has 16 gigs of RAM, but in terms of hard drive space, I think I've got 1.5 terabytes of hard drive space. So I'm looking at having approximately 1,000. Is that 1,000? That's about 100 times more hard drive space than I have RAM space, which means that I can't store everything I want in my RAM. I only use it part of the time. So this scale of difference is that we get onto the CPU. The CPU itself has some memory on it. So you would have heard of, maybe you would have heard of cache on a CPU. So some people sell CPUs based on how much cache they have on them. Cache is then like, I'm roughly hand waving a lot of this stuff, but roughly like 1,000 times faster than RAM. And the CPU registers are very, very small pieces of memory that are the actual bits of memory that the CPU is working on at the time. So you get this kind of thing where the registers and the cache only work when the CPU is running. The RAM only works when there's power to the RAM, and the hard drives can store information whether or not they have power. But you get this kind of thing where each one is, I use the number 1,000, but I'm not tied to that number in any way. If I want to be really scientific about this, I would say each step in this chain is an order of magnitude faster, but also an order of magnitude slower than the other steps before it in the chain. So you get this situation where the perfect computer, if we could get one, would have power all the time and would have like CPU registers and cache as its only storage. This perfect computer would probably cost about $1 million. I'm sure there's a few of them around the world that exist that are like that, and they're used for very specific purposes. I don't even know of them. I would assume it's some kind of military thing or something like that, because even in the most high performing situations, we still usually use this setup because it's not that much slower than if we tried to build a computer that was entirely like that. I mean, we'd have a really interesting issue with registers and cache, where the more of them we tried to make, we would actually get a delay in how fast our CPU is running based on the speed of light to move data back and forth those few centimeters. So yeah, there's some weird stuff like that. And Tom's saying stuff like that is used for trading. Adam's asking what type of data goes into the cache. What goes into the cache is usually, what are you using right now? So the exact instruction that you're executing right now, it will be in cache. The exact variable you're reading right now will be in cache. I'll talk about that in a second, actually. Oh, Raymond's asking, is stuff like this going to be in the assignment? No, not necessarily. This is stuff that I'm teaching because it's fundamental to understanding how computers work, and you might learn more about this later. In fact, just this slide here about memory is me doing an overview of what in another course, like say for example the operating systems course, you'd spend a few weeks on this kind of structure and learning about it. But I just wanted to tell people about it so that you know about it. But you won't have to use it in 1511. It's more that 1511 is an introduction to the world of computing, and this stuff is reasonably important for that. Yes. Okay, so details of what we're doing and how we use memory. So the hard drive is where our files are stored. So any file that you've created, which is like program.c, or you've used DCC to compile that into a running program, so like my dice check, for example, those files are always stored on the hard drive. So the code files as well as the programs are stored on the hard drive. When we want to use our programs, so when we run our program, the first thing that happens is it gets copied into RAM. So it gets copied somewhere that says, all right, this is the program that's going to run now, and alongside the instructions that go on in time is a bunch of other stuff that's going to get used in the program. I've got a slide for that in a second, actually. I'll show you that. Our CPU will then go through those instructions one at a time and will read those instructions from the RAM, put them on the cache, and then say, okay, reading from the cache, I am now going to do this particular instruction. When it's done with that instruction, throws it away, grabs the next one, puts it in the cache. Everything that we do with variables is stored somewhere in memory as well, so you can consider a piece of the RAM in our computer that we're using to run our programs is going to have, it's going to be given to us, and it's going to have everything in it. Actually, I'll go to the next slide and show you that. So anytime we change variables, or anytime we create a new variable, a piece of memory in our RAM will be created for us to use. So, oops, I'm gonna move. There's nowhere for my face here. I'm gonna put my face half off the screen for a second. If I duck, there you go. You can still see my face now. So this is, and I should also reiterate that a lot of this stuff is just useful knowledge. We're going to be testing you in 1511 on your ability to use C. This may or may not help your ability to use C, knowing these fundamentals. In the future, it will, like if you're going to continue on with programming, this stuff will become vitally important. But for now, we can sort of gloss over it as I'm doing. And you'll learn about how to use C without necessarily knowing all of this. But once you get even a little way into programming, this stuff becomes necessary. So, when we run a program, we say to our operating system, I would like to start this program. So the operating system says, yes, here's some memory, and you can use this memory to do stuff. First thing is we copy all of our instructions into memory. So if memory is a series of ones and zeros, this will be the top, this will be the first memory address that we're using to store stuff, and then we'll go down until the end. When we get into actually using memory, which we'll be looking at doing things like grabbing pieces of memory and using them, we'll see how big this chunk of memory actually is and what we can do. So the first thing is our programming gets copied in there. And then some space gets reserved after that for variables that have been declared, so variables that the compiler can see are definitely going to be needed. So all your ints and your ints and doubles or whatever that you've declared specifically in your code will be put into this chunk of memory here. And then we'll also have two sections here. One's known as the stack. The stack actually builds upwards from the other end, and it says, where are we in our code? We're going to go into this in a little bit more detail later. We're going to learn what a stack is as well. But basically, it's a way of organizing our information to know where we are in the code. So it knows which if statement we're in, which while loop we're in. It knows what line we're up to, roughly what line we're up to. Because once you compile something with DCC, the notion of the lines of written code is not quite the same anymore. It's more like, which instruction are we performing? Because when it comes down to it, when we write a line of code, you know how I've seen like, if this or this, this and this is greater than or equal to this, you'll see that things get done in order. Like we would sort out all the maths first, and then we'd do the inequalities and stuff. So they would all be separated into instructions here, and we know which one we're up to in the stack. So as the program runs, the stack changes size, changes shape, and then we have this empty space here, which is called the heap. Don't worry about the names, not super important yet. I'm giving you the technical terms for all these things because I know that there's a significant percentage of you that are definitely going to need these in the future, are going to need to know what these things are. But don't worry if you forget them immediately, because anytime that you learn about these again, you'll get given their names again. But the heap is empty space, and empty space can be used to store things once our program starts running. We'll be using that later in the term. We won't be just declaring variables the way we have been before. Sometimes we will explicitly say, yeah, I'm going to grab this piece of memory and now it's mine and I'm going to use it for stuff. Oh, interesting, Girachan. Does a compiled program use less, more, or the same memory of a C file? There's no guarantee. So sometimes in C we can use a very small number of letters to ask our computer to do a whole bunch of different calculations. So when I was talking about, those single line which has check this maths or this and this or this and this maths, that will actually probably blow out to being larger in compiled code than we wrote it. But if we're doing something along the lines of I'm putting a whole lot of white space and a bunch of comments and stuff in order to explain something, and then the code is very small, the compiler is going to throw away all of my comments and stuff. So you can't really necessarily measure the size of the code file versus the size of the program. Okay, so I'm going to move on. And this is something that I think came up a little bit in questions there. So Raymond was asking about the theory and stuff. I think Megatz was... Oh, no, wait. Oh, no. Megatz was asking about something else. Hopefully Tom's answered that. Tom has answered that. Yeah. Okay. So I want to say there's a whole lot more to talk about here. Because what I've done then is I've just spent 20 minutes trying to cover both the theory of computation and the physical structure of a modern computer. I would say both of those topics are the kind of things you would consider to be 10-year topics. For me personally, I spent a good, say, 5 years learning about the theory of computation. So about what it means to compute at a level where you don't even use a computer. You just think about what it means to execute instructions and what does it mean to store information and things like that. So we can nearly think about that as a philosophical pursuit. And that's the kind of thing where when I call these things 10-year things, I mean like you could spend 10 years on it and still be learning new stuff. So me spending 20 minutes on it here is just the barest of introductions to these kinds of things. And the other side of this, the hardware side of how this works, just that slide on memory, the way that a program is laid out in memory, those are also 10-year kind of things where to get full mastery of how these things work to the point where you'd understand how to build an operating system, for example, to how to manage memory like that. Those things are also kind of 10-year ideas where at the end of 10 years you could say there's still more to learn about this. So I wanted to drop some ideas for you so that you can maybe in the future develop these things a bit more, and if not, you can still think about these things while you're using computers, because I think they're such complex things and they're so important to us. It's good for us to have at least a reasonable understanding of what's happening inside. So I'm talking about lifetime learning here, but for the moment we're going to go back to using C, so I'm just going to go back to teaching C now. But I want you to think about some of these things as we're going on, because when it comes down to it, it's that little man walking backwards and forwards with the box and chalking stuff on the ground. When it comes down to it, if you can think about that and the complexity of doing that, and also the possibilities for what you can do when you've got a system that simple. Um, some of that way of thinking will help you in terms of how you're actually going to do your programming. So that's all I want to say about that stuff. And I do want to say that there's just so much more. I haven't even scratched the surface here. And also, I'm going to say that everything that I've said today is very hand wavy, where all I've done is said, look, here's a vague overview of what it is. If you wanted to pick at what I was saying for some of those things, some of it you could say, look, that's not really factually correct. And I was like, yeah, okay. It's because I glossed over a lot of that stuff just to make sure that you have the vague idea of it. Okay, so continuing on to some more technical C programming, and I don't really, and I should remind everyone that this course is not just about programming in C. Um, when you reach the end of this course, I hope that everyone, once we reach the end of this course, will understand more about computers in general, but also understand more about programming to the point where before you did this course, if you wanted to teach yourself a programming language, there would be a certain level of difficulty involved, a certain amount of time it would take to do it. After you've done this course, what I hope is, regardless of how well you know C, your ability to learn a different programming language will be much better than it was. So everything we're going to teach you is going to be like this sort of fundamental ideas of programming, and we're going to look at C. So when I say we're going to do something technical in C, it's also this idea that hopefully I'm going to teach you more than just how to do something in C. Let's see how we go. I think I'm about to start freestyle rapping about C again. Okay, so yeah, so Gabriel's asking, after learning C, will Python be easy to pick up? I think it will, because a lot of what I'm teaching you here is fundamental to what programming is. So if you learn how to do loops, it doesn't matter which language you learn how to do loops in. A lot of the stuff you learn is how to solve problems with repeating code. And all of that, when we think about how much time we spend programming, um, a significant amount of time is spent thinking about how you want the program to function, and then you spend some time translating how you wanted it to function into the specific language you're using. So the only thing you have to learn is how to translate your thoughts into Python. And then all the stuff we're teaching about how do you solve problems with loops, that stuff is stuff you already know. So what I find is that it is still hard. It's not something that's just gets stupidly easy. But the first language that you learn is where you learn how to program. The second language you learn is where you learn how to just translate something into code quickly. And then from then on, every language you learn after that is much, much easier. Because by then, I think it's nearly the point where you could say once someone's learned two languages, they're like a programmer. They've reached a point where once you've reapplied your first programming learning to a second language, you've learned how to reapply your learning. And when we think about it, learning how to reapply your learning to new situations is what we would consider mastery, the capability to then go and solve any problem with your skills. So that's I think I do like that question of like, it will Python be easier after you've learned this? And I think I hope the answer is yes. I hope for everyone who's getting deep into this that the answer is that every other programming language after C, after learning 1511, will be easier. Especially because I hope that the way I'm teaching this is not just how to do things in C. So I'm not just giving you code and asking you to repeat it. I'm trying to talk about the theory of why we use things and how we use them, and then translating it into C. So hopefully we get to that. Ding, grats, everybody. You have now gained XP, and now you can spend skill points, and you don't have to spend your skill points on C programming. So it's not the Elder Scrolls style where you only get skill points in what you've been working on. You can then spend skill points on learning other things instead. Okay. Back on topic, although I thought that was a really good question, so I do like to jump to really good questions when they turn up. So, what happens when we need a series of variables together that that work for the same purpose, so they're the same type. So I've got a whole bunch of integers together that I want to use as a collection of integers rather than just a single integer. And what if I want to be able to process them all as a group? The way that we're doing things at the moment with ints and doubles doesn't entirely work. So we can't collect them together in a nice way that we can use them. So let's have a look at an example here. So I've collected together the final marks for all the students in COMP1511. So we're looking into the future here, or we can say I'm looking into the past of the people who have done it in the terms before. So I could if I wanted to. I mean, based on what I've taught you so far, this is my only option. I've got a whole series of integers, and those integers are the marks for the students. These could be doubles as well, depending on what kind of fractional amounts that I want for all the students, but let's just call them integers for now to keep it simple. So I've declared all these integers, and I'm going to store all the marks for everyone. So I'll just make sure I'm not blocking any of the words. I'm not. Yep. If I want to test all of these ints to see who's passed or who hasn't, I mean, if I've got, what are we at? We're at around 500 people at the moment in the course. So I've declared 500 integers, and already at this point, my copy-paste fingers are hurting from having to do that 500 times, and I've had to go through and change the name of each of them so that they're different. I'm already so tired of this, and I never want to program anything like this ever again. Obviously, I didn't do that. I've just put an etc here. But imagine having to declare 500 integers with different variable names. That's already too much. I would already consider that to be beyond what I would ever want to do as a programmer, and that kind of repetitive work for a human is just a really silly idea to even do, because the computer is made to be able to do repetitive work, so we should be able to do this in the computer some way instead. That's just making these variables. The other thing is I can't loop through these. There's no way to run a loop of code and say every time I loop this code I want to change the name of the variable that I'm accessing somewhere else. That's not actually possible. I can't say access marks student 1 now access marks student 2 the second time I go through. I can't change which variable the loop looks at. So what I would have to do is I would have to rewrite this same code each time with a different variable name, checking if that's over 50. So I would have to do the same thing and copy paste 500 times and then just change the variable name in each of them. So obviously this is my example to show you that this is not working like this. So my solution to this, and it's not my solution, C's solution to this, and also most programming languages are going to have the same thing. People are talking about lists in chat. They have lots of different names. Lists, arrays, vectors, other structures like that. They're not all the same, by the way, so they do have different names for a reason, because they actually act differently. But the one I'm going to show you for C is an array, and it's a specific structure in memory that we use. So an array is a collection of variables, and one of the things that we can do with an array is we can access a large number of variables with a single variable name. So we say, instead of saying each of these has an individual name, they're all under one umbrella of a name. And then we can loop through this collection and we go from one to the next, and we can look at all the values inside it. So this way I could store 500 marks in an array, and then I could have a program that would go through them one at a time and read the number and say, has this student passed or not? As we go deeper into the course, we'll have much more complex structures that can do this in better ways, but for now we're going to look at an array that stores multiple of the same type of information. So getting into the details of what this array is. When we're looking at variables, where we're taking a small amount of memory for a single variable. So all that we've done so far with variables is have single elements, like this integer here, 32 bits worth of memory. But an array is a big chunk of memory instead of just that single piece. It's a large piece of memory that is a multiple of these integer-sized chunks. So we have Here, for example, 5 of them at once. So instead of it being 32 bits of memory, what's 5 times 32 is 150, 160. I had to do that in my head. Wait, is it 160? Yeah, I think it's 160. It also doesn't matter. I'll use a calculator if I need to. This is actually one of the funniest things about computer scientists. He asks us to do maths by hand, and we're like, we don't do that. That's why we have computers. It's like, and even simple maths that we should be able to do, we start to do it less. Start to do it on computers instead. Anyway, so this is a big chunk of memory that you could say is theoretically separated into 32-bit chunks, and each one of those contains an integer. When we use arrays, all of the variables we have inside them are the same. So I can't have int double, int double. I will show you structures that we can use for that later on, but for now, arrays, every element in the array is identical. And we do that so that when we loop through the array, we expect that everything inside is the same, as we use the same code to access each element. The individual elements in an array do not get a variable name. There is one variable name, and it covers the entire chunk of memory, that's the array. And instead of accessing each one by a name, we access each one by a number. The nice thing about this, and this ties in with everything we've been doing with looping and stuff, is if we're accessing each element inside the array by a number, we've already got a technique with our while loops to take a number that starts at 0 and counts upwards and goes up 1 every time we loop. And if it goes up 1, it can access a different part of the array. And you can now do a while loop that goes through an array, accessing every element in the array. So let's look at some of the details of declaring an array. It is very, very much like declaring a variable. And once we get into the idea of what arrays are, we will start to consider arrays as just a variable. An array is just a different kind of variable. But for the moment, we're kind of separating them so you can learn the concept. So it has a type because it's a variable. This isn't just the type of the array. This is the type of each individual element inside the array. So all the variables stored inside the array are of this type. And then I am introducing a new symbol, one that we haven't used before in C, but you will get used to it because we're going to be using arrays a fair bit, is the square brackets. The square brackets is the signifier of an array. So anytime you see a square brackets in your code, it means something's happening with arrays. So there's something happening with chunks of, I don't necessarily want to say chunks of variables, but I could say chunks of integers or chunks of doubles or chunks of storage in memory. We're going to be using the square brackets to signify that. So when we declare an array, the square brackets with a number inside will be saying to us how many of this element type are in this array. So this thing here declares an array that can hold 10 integers. So this is exactly 320 bits of information separated into 10 sections that store integers. Wait, what's the... Oh, people are talking about memes. I'm gonna let you talk about memes. I don't know if I have any memes today. The memes are scattered through the lectures based on whether I can think up something that I want to put in as a meme, rather than me trying to put a meme in every single lecture. It's usually the one pops into my head and then it goes in. Okay, then afterwards, initialization is weird. Right, so initialization of variables was easy because every variable just stored a value. But an array is storing multiple different values, and so it's harder to write that down. I'll give you two options here that we can use. There are more options than this, but I'm going to try to keep it reasonably simple to begin with. A lot of the time when we're creating integers and we don't know what value they're supposed to have, we can just give them a generic value. So we could just declare them as 0. There's a way to do this easily for an array where we have the curly brackets here and we put a 0 in the middle. This is going to zero out the array. This is a special command. What it's going to do is it's going to take all of the 10 integers in there and set them all to 0. So it's going to go through and just set them all to 0. If you don't want them all to be 0, you can give them individual values. So here I have a an example where they're counting from 0 through to 9, but you could put any values in here and declare your array to have a whole series of different values. This is an all or nothing thing. So either you set it all to zeros or you set it all to specific values. There are some techniques in between you can do for other things, but I'm going to leave it like this for now so that we don't confuse ourselves too much. Also, when I'm setting everything to zeros like this, you can't even give this another number. So I can't say go through and set everything to 4, for example. That just for C doesn't happen to work like that. So either we say I don't really want values for all of these things and just zero out the whole lot, or I do want values for these things and here are all of the specific values. So for the moment, choose between those. And if you want to, you can look up a lot of the other possible weirdness that can be used for initializing an array as you declare it, but I would also say that you don't need most of that stuff if you don't want to. So a lot of the time I will just initialize all arrays with zeros, and then if I want specific values in there, I'll go in afterwards in code and I'll access individual elements of the array and change them. Some questions about zeroing and... Oh, I'm going to let Tom answer those questions in there. Okay, so let's look at some detail about how to access elements in this array. So at the moment, we know what an array is, and we've seen enough C code to be able to declare the array, but we haven't yet seen anything about how to use the array. So every part of the array that is like a single variable is not exactly the same as a single variable, but it's like a single variable, is considered an element of the array. So this array has 10 elements. The elements will be accessed via an index. This is an integer, which is their address inside the array. So I've got 10 of these, they're at these addresses. The interesting thing is indexes start from 0. So it's a weird thing because you look at it and you just go, why do we count from 0? This is obviously the first one. Why isn't this number 1? And then this number 2 through to 10, right? So in a human sense, we think that that is something that makes sense to us. But if we think about it a different way, you'll see why this thing is. So the array actually gives us the first element, because the array actually says this is where the first element is. This is where this big block of memory starts. And the first element starts at the very start of the block of memory. There's no other random stuff in between. There's no housekeeping for what the array is. The array just says this is where the first element is and this is how many there's supposed to be. So the index actually says how far do you want to jump into the array to see more. So for example, if I say I'm not jumping any further into the array, I get the first element. That's why the first element is 0. And this number 2 here says jump over 2 elements to get to this one. So as opposed to numbering the elements in terms of like this order that we might do as humans, the way we index them is actually how far did you want to jump into this array. So we've got a block of memory with lots of integers in it. How far into that memory are we going before we stop? So this one's at the very start of the memory, so I'm saying 0 because we don't move into the memory at all. We read from the very beginning. And this is number 5 because we jumped over 5 elements to get to it. So that's why we're counting that way, because that's actually how the computer is accessing these things. So we go to the array, which points at the first element basically and says, okay, here's my memory, here's the first element here. Look at that thing, and then jump a certain number of elements in and look at another thing. So that's how we access things via index. The easiest way to remember it really is just say arrays always start at 0, and to access any element in it we use a number that goes from 0 and counts upwards. So for example, the element number 2 is not the second element, it's element number 2 reads this one, right? I think this is something you're just going to get used to as you go along, and it's all part of the mic check thing, right? It's like, why does Mark keep mic checking from 0? And it's because 0 is a useful value and we're actually going to be using it. We're going to be counting from 0 a lot. So here's some C code for accessing elements. So here is my declaration of the array, and this is where I want to talk a little bit about the square brackets. So when I'm declaring an integer, the square brackets and the number in the square brackets there says how many integers are going to be stored in this array. So I declare this saying this thing can hold 10, and they're all zeros. So I've got an array the size 10 that's all zeros. Then, after I have declared the array, the square brackets change. So they now have a different purpose. So this is important to know that the square brackets don't always do the same thing. I think this is the first time we've seen this, because in everything else we've done with our code, if you ever see a symbol, it always just does the thing it does. But now we're looking at a symbol that has a different purpose depending on how it's used. So if it's used in declaration, declaration means I'm making a new variable. So when I make a new variable, it starts with the variable type. If I'm not making a new variable, so there's no variable type here, this square brackets is no longer saying how big the variable is. It's now saying which bit of the variable I want to read. So how far into the variable do I want to go? So this line here says array of marks square brackets 0. This is me saying look at that array and don't jump any further into the array. So we're looking at the first element of the array, and then we're saying it equals 85. And this is a normal variable assignment. So once we've accessed one part of the array, it's exactly the same as accessing an integer of that type. So accessing the first element of the array, this is just the same as any other integer variable that I might use. Any other single variable, I can set it to a value. I can also read its value. I can do all this other stuff with it. If I want to access a particular element of the array, it is an integer index to do that. But we can also access an individual element of array using the value of a variable. So I can have an integer variable here called the access index. You can name these whatever you want. We're probably not going to be calling them access index. That's a little bit wordy for what we would be using. But if I set this to 3, and then I use that variable inside the square brackets, I will get variable number 3 from my array, which is the 4th element of the variable, of the array, and I can set that to 50. So the continuation of that is, if I do the name of the array, square brackets, and a number, I'm accessing an individual element, which means I can do cool stuff with those as if they're integers, and I can say take the value from number 6 and copy it over number 2. So I can assign the value of 6 to the value of 2 in the array, because once I've accessed them using the square brackets, they're treated just like variables. So this is like me having two variables, x and y, and saying copy the value of y over x. You know, so we can do the same thing with the arrays. Some things will cause errors when we're trying to do stuff with arrays. If I have an array of size 10, these are my valid indexes, 0 through to 9. So 0 through to 9 says these are the pieces of the memory that I can use in that array. If I try to access element number 10, I've gone off the end of the memory, because number 10 is not the 10th element, it's this idea of this 11th element. And so if I do that and I try to set it to something, my computer will say you can't do that. The array of marks array, the variable that is the array of marks, I mean, this is the problem with me naming a variable of its kind of type, does not have an element number 10. You have gone outside of the memory allocated to that array, and if you're trying to affect that memory, you shouldn't be able to. This is actually super old school, because this is a way that people used to hack programs, where you would take something that was supposed to access an array and you would change the index to go outside the bounds of the array. And if you knew well enough how to get outside the bounds of the array into other parts of the program, you could rewrite the actual instructions of the program. Because if we remember, if I go back to here, declared variables here and the instructions are there. So there's a possibility, if I change the index by exactly the right value, I can come back here into the instructions and I can insert code into the instructions pretending that I was accessing the array. That was years ago though. I think that was like back in the 80s, before we started protecting arrays against that kind of access. With the programs you're doing with DCC, this will throw an error. It won't allow you to just write code over another part of the array like that. Ruby's asking if the array size can be dynamic. No, arrays are fixed because they're actually chunks of memory. So we can't have a chunk of memory that can change size like that, because if I've allocated a chunk of memory for the array, and then I start putting stuff next to it, so I declare other variables afterwards, I can't then expand into that bit of memory. So arrays are specifically made like that because when all the memory is together in one chunk, it's actually much easier for the computer to process it. So there's a bit of back and forth of why we use this. If you get really a lot deeper into computing and things, and we start thinking about how efficient our code is, and I was rapping about that today, even though we're not discussing efficiency in 1511. There's enough to learn as it is. But if you're trying to be really efficient, having memory that's in blocks together is much faster for the computer, because the computer can grab this entire array, chuck it in the cache, and then work through it all without having to go back to the RAM. And as I was saying, the RAM's like 1,000 times slower than the cache, which means that the CPU is sitting there waiting while things get pulled out of RAM. When we think about how long it takes your computer to get stuff off a hard drive, your CPU can legitimately be wasting thousands of possible calculations just waiting for something to come off the hard drive, go through the RAM and into the cache to be used. So there's lots of little things like that. We're not really going to go into that though. I think for the moment, the important thing is get your C working. It doesn't matter if it takes longer to run than other possible C programs. At the moment in 1511, we're just trying to get stuff working. And also the difference between something that runs in like 20 milliseconds and something that runs in 500 milliseconds, you're barely going to notice. So we're not too worried about that at the moment. Okay, so thinking about reading and writing arrays. So we want to think about the idea of being able to print out a whole array or scanf a whole array, because if we're going to start using these things as collections, it would be nice to be able to say, all right, just dump this whole array to the screen so that the user can read it, or get the user to type in 10 numbers and we'll put all those numbers in the array. One of the things that we can't do with C is print the whole array or scan a whole line of text into the array just on their own. However, we can do it for individual elements. So if we can do it for individual elements and we know how to loop, then we can pretty easily print out all the elements in an array, or we can pretty easily scan everything into an array. So if we're going to do input and output, there's a couple of things that won't necessarily work. So if I'm trying to scan in multiple elements into an array like this, I can't just go scan in 10 elements and chuck all of them into the array. What we'd have to do is do them separately. Having said that, if we want to do an individual element at a time, that's pretty easy. We can do that because, as I said, once you've used the square brackets and you've accessed one of the elements of the array, you treat it exactly the same as a single variable of that type. So once I've used the square brackets and said, give me the third element, element number 2 in the array, this thing now is treated just like an integer. So it's a single integer, which means we can scanf into it just the same way we would scanf into the location of any other single variable. So the arrays, once we've grabbed an individual element of the array, we treat it just like a normal variable. We can print out in the same way, so we can say the fifth element here with the index of 4 can be treated the same way as a single integer if it's an integer array. Obviously you can have arrays of doubles and things like that as well. Alright, so this code here will not work because I have not accessed a single element. All I have here is an idea of a collection of them, and I can't just put multiple numbers into the idea of the collection. Okay, 12:04, it's a good time for a break. I'm going to continue with a little bit more arrays, but then we're also going to do some code today, so I've saved the last hour to do some code to show you some demos, not just of arrays, but of functions as well, because we talked about functions last week. Let's have a quick look at some of the questions we have. Yeah, the questions like I think Miguel and Ruby and others were talking about specific size of arrays. Arrays are going to be fixed once we write them. Um, See if we're talking about if it's red, it goes faster. All right, I don't think I need to talk about that in terms of the lecture. Okay, so break time. I'm going to leave you with this slide for a little bit. If you don't know XKCD, it's a web comic where they um, talk about a lot of the funny little issues with uh, with computing and programming and things. So a lot of what we're getting into, and especially some of the stuff we talked about last week, and some of the stuff we're starting to think about, when there's lots of different ways to solve problems, it's hard to know exactly how you're going to do it. So for the moment, don't worry. Try to get code that works. Um, Try to get code that can be modified and reused. Don't worry too much about how elegantly it solves the problems. That's something that comes over time. Uh, but it's good to know, I think, that the struggle to write code that is good code that works really well for you is something that we as programmers are constantly struggling with. Okay, let's go on break. 6 past 12. We'll come back at 10 past 12, and at 10 past 12 we're going to continue, and we're going to have a quick look at actually using some arrays and some functions in a program. Yes. Sorry, I just felt like doing that. Chicken said, he's gone and I'm in charge now. This is my course. She's very, very lazy. Like, it's actually quite funny because it depends on uh, it depends on the time that the lecture is. So this particular cohort, your term three cohort, is going to know Chicken as this lazy, sloppy cat who's just always just sort of having a nap somewhere. And anyone who has had the course in the past, who has had an afternoon lecture, thinks Chicken is like a super, super vocal cat that is always asking for food. Because it really depends on the time of day that you meet Chicken. Okay. Miguel's. We were talking about whether or not to use arrays that are too big. There's a constant struggle. So there's a constant struggle in programming when we try to make programs run fast or take up less space. And usually it swings back and forth. It's a seesaw of one or the other. So a lot of the time we can take up more space in memory in order for the CPU to do less work. You know, we're talking about the two things. This is back to the fundamentals of what computers are. They have a thinking bit and a remembering bit. You can burden one of those more to unburden the other. So if we remember more things, we can sometimes use CPU, less CPU cycles to do things. So we can take up more space for a program to run faster, or we can take up less space if we're running out of space, and get the processor to do more work. So there's always going to be this back and forth. So one thing that we were talking about there is like, what about if we don't know how much space we're going to need for an array, so we make a really big one just in case. So that kind of thing works pretty well because the idea of grabbing a piece of memory from the computer shifts you from the CPU, which is fast, into memory, which is like 1,000 times slower. So if you're willing to take that 1,000 times slower hit and ask for memory while the program is running, then you can do so. But if you don't want to take that hit, you can say, while we're setting up the program, just grab a big chunk of memory and we'll deal with it later. But it'll be available for us to use, which means we will never take that hit of having to allocate new memory. So there's this back and forth. Having said that, all that stuff is pretty super advanced and we don't need to worry about it right now. We will be doing some allocation of memory in this course, so it's good to know that at some point we will grab memory as the program's running. But whether we're trying to make stuff run fast and things like that, we're not going to worry about that at this point. We're worrying about learning how to solve problems with code, which I think is more important at the beginning than learning how to make those solutions run in different ways. So when you get very advanced in computer science, you don't just solve a problem. You solve a problem the fastest way it can be solved. Or you solve a problem so it fits on the processing capability of like an Arduino sitting behind the dashboard of a car or something like, like different things like that. Okay. Kat's asking if there is a limit to how big your array can be. Yeah, so the integer size will... The integer size is not actually a limitation to the array size. I think the limitation would actually be how much memory each program can have. And I think that depends on your operating system. Older operating systems will give you 2 gigabytes of memory for your program to run in. More modern operating systems, like the one we're using, a modern Linux, like we're using in the computer labs, will give you, I think, up to 8 gigabytes of memory. And so it'll be depending on the size of your variables and how many of them you have, whether or not you'll use up all that memory. Okay, let us... I'm going to move my face up there. Let's put together an array. So, you'll notice that all of my examples... Oh, not all of my examples are gaming. Actually, maybe all of my examples are gaming. I like playing computer games. I have other people like playing computer games too, because they're a lot of fun. Speaking of which, Star Wars Squadrons came out like at about 2 a.m. last night, so you're wasting teachers' valuable time right now. I should be shooting down TIE fighters right now. Anyway, let's make a program to track the scores of players in a game. So we're going to keep this simple for the moment. We're going to do a simple 4-player game. I mean, there's heaps of 4-player games out there, so 4 is a nice number for this. So we want to be able to set people's scores to certain values. We want to be able to display their scores. Um, and we also maybe want to check who's winning or losing the game. And if it's a co-op game where all the scores are added up, we want to be able to see the total. So this is a way of me showing us arrays. So we'll have an array with 4 people in it, and also some of the things we can do when we loop through the array. Um, Yeah, and Miguel's talking about the 32-bit and 64-bit difference. This is why we're in 64 bits at the moment, because 32 bits. So you know that number we were looking at, 2 trillion. That's 2 gigabytes. 2 to the power of 32 is roughly 2 gigabytes, which when we were using 32-bit computers, and some people still have 32-bit computers here and there, that was the maximum amount of memory that we could address in one space at a time, which meant even if you put more RAM chips in your computer, you could still only look at 2 gigabytes of RAM at a time, which meant that each program was limited to 2 gigabyte size. And we hit that point, and we were like, my full-on massively multiplayer computer game, World of Warcraft won't fit in 2 gigs. I don't think that's the only program that spurred that change, but we realized that we needed to make programs that were bigger than 2 gigabytes at a time. Like heaps of programs nowadays will use more than 2 gigabytes at a time. So that's why we went to 64-bit. And the difference, it's interesting, right? Because you go 32-bit, 64-bit. Is that double? It's like, no. That's double the number of bits in a number. And every bit doubles the size of the number. So it's 2 to the power, like it's in the order of magnitude, 32 orders of magnitude bigger as a number. So now we have basically no limitation on the amount of RAM that we can address at a time. Our limitations now are how much RAM do we actually have to use. So I know most computers nowadays 16 to 32 gigs, but you get away with even 4 or 8 gigs and still be able to run a lot of things. But you can address all of it at once if you need to. Okay, so back to the game itself. 4 players. We want to be able to individually set their scores to different values, but we also want to be able to loop through, see who's winning and losing and stuff like that. So the individual elements, every problem that we have should be broken down into parts, and we should solve them separately. So the first thing that we want to do, if we want to store 4 people's scores, and we want to treat those scores as a group of values that we can use together, we'll create an array for that. This first part of the problem to solve is always easy because whenever I show you a piece of code, it's always going to be, what have we just talked about in the lecture? That's what we're going to do. If we're going to access individual players, we'll do them via their index. So we have, for this example, players 0, 1, 2, and 3, and we're just going to use those for their player IDs. In a sense. I mean, if we want to, we can think about giving them names and stuff like that, but we're not going to go into that because I haven't talked about using letters yet. Anyone who's done a bit of programming before will have seen characters and strings and stuff, but we'll get to that. I think that learning about the fundamental structures of how to move things around in code and store things are more important for the moment than how many different things we can do. So if we are trying to access all of the players' information at once, we're going to need to be able to loop through the list and look at each one in turn. So there's no way we're going to try to look at all 4 at a time. We're going to look at them each individually, but we're going to learn about looping through an array and then getting information from the array as we loop through. See Tom? Tom's probably setting up his tute today. I don't know if Tom teaches on Fridays. I'm not sure. Ooh. People talking about making music with computers and stuff. I used to produce drum and bass back in the day. Do people even do drum and bass anymore? It's like we got. I think drum and bass got nearly erased by dubstep about 10 years ago. Okay, so we're going to loop through to access individual players' scores, and a lot of the things we're doing. So the ability to see who's winning and losing, we're going to do those with loops. The ability to print out what people's current scores are, we're going to do those with loops as well. So what I want to show you today is, if we have an array, some of the cool things we can do with loops and the array. So this is the kind of thing we're building up This program is going to use everything that we know because it's going to use variables and it's going to use loops, and now it's going to use them with the array, and we'll see how it all kind of combines together. So let's jump. I'm not gonna follow the slides that closely while I'm writing code. Let's jump into VLab. Go to my COMP1511 directory. I don't have a lecture created for lecture 6 yet, so I will make one. And I will make a brand new file. What shall I call this? Playerscores.c. Okay, so I have a new file called playerscores. Track for players' scores in a game. We want to be able to store integer scores. Actually, let's format that in a particular way. I'm going to do like a little dot point list here. So we're going to be able to store their scores, print out everyone's current score, say who's winning, maybe print out the total of all the scores. I don't know if we're going to get to that today. I think if we get the first 3, that's good. Maybe I'm going to put a question mark onto this. Maybe to do. Should tell you something that's really cool that you can do with a lot of text editors. If you type in the word to do, well, I guess it's a phrase because it's technically 2 words joined together. It gets highlighted like this, specially. So what you can do is you can leave markers in there for yourself saying, I want to do this later. I've just got to remind myself that I need to do this later, but right now I need to work on something else. So you put a to-do in there, and then you can scan through your code, look for these bright yellow, bolded, highlighted words, and you go, okay, that was the bit that I said I was going to do later. So it's made by me. I don't know how Chi just auto-completed to player, but I guess my new name is Mark Player. Maybe that's my programmer rapper MC name. Oh, I should say. Oh no, I'm gonna put my email address here before I put the date. Yeah, we're in October. Okay, standard setup for a program. I am expecting to print stuff out to the terminal because I know that I'm gonna do stuff like here, so print everyone's current score. So I am expecting to use my standard input-output. Got my main. I can put my return 0 at the end. I can actually do this. Actually, you know, did I do this with or without it last time? I'm going to do it without it this time to show you that it doesn't really make a difference whether it's there or not. It's sort of a legacy thing, the return 0, that not everyone uses anymore these days. So I want to show you that sometimes it's necessary, sometimes it isn't. Sorry, what I should say is it's not always necessary. You can just put it in if you want to. Here we have a program, as I said before. This runs. I just make sure that I've done all my setup and I've closed all my brackets before I start doing anything. Okay. Jaws is saying my drum and bass career died, so I became a rapper. I have an album that I played on that's on Spotify, actually. just a little aside, I played bass on an album and it's there somewhere. It's really hard to find because you can't find it by my name. One day I'll tell people. Anyway, let's get into this and let's think about some of the stuff that we talked about in our style to say that we can put some comments in first before we write code. So I can say, Declare an array of 4 integers set up initial values. I'm not sure. We'll see how we go. So the first thing I'm going to do is the array which has 4. So I'm going to call that scores. So at the moment, if I was going to do this, it would be a single integer. If I want this to be multiple integers, I need a square bracket here, and I need to say how many. So I'm going to say 4. Let's think about this a bit carefully. Maybe I don't want the number 4. So nearly any time that I write a number in my code, I get a bit scared because I think, well, what if I want to change that later? What if this becomes, what if we get DLC, and in the DLC we can add a 5th player to the game? So maybe I want to future-proof myself for the possibility of the number of players changing, and I say number of players for the moment is 4. But if I want to change it, I want to be able to just change num players here to 5, and then hopefully everywhere else in the program it'll change. I don't know if that's going to work. Sorry, I just changed it to 5. DLC came out early. I don't know if that's necessarily going to work for all the code that I've written, but for the moment I think that this is a nice thing to do, which will maybe help me later. If I want to initialize this, there's a few different things I could do. So I could give everyone a starting score of 0. That's a fair enough way to do things. Another way that I could do this is I could say, why don't I give them their starting scores? What if there's some kind of handicap, for example, and this was based on people's prior rankings in games, what score they should start off with. So this person's very experienced, they should start at a lower score so that they can balance with everyone else. This person's like their first game, so they get to start with a really high score or something. You know, we could do something like that if we wanted to. So this is an example of me saying, if I want to initialize this, I could have initialized them all as zeros, or I can initialize them as values. If I want to set up initial values in a different way, I've got that in the slides here, I could go through these directly and assign their values one at a time like this. And so I might show you that as well, just so that we get the idea of how we access individual elements in the array. So scores 0, and this is where the idea of num players and this wouldn't necessarily work the same way. Because if I'm doing exact numbers here, then I don't know what's going to happen if I change the number of players. For example, if I change this to 0, this code and this code will both stop working. So we're not super tied to the ability to change here, but I still like having a defined number. So I could say score 0 is actually, let's say I wanted to bump everyone at the start of the game because they bumped up the difficulty. So this one goes up to 55. The second player goes up to 17. I'm just arbitrarily choosing things here. It's not, this is not tied too much to what we're trying to solve as the problem. As programmers, I just want to show you that there's a way of setting up the values here, and there's another way of accessing each of the values if we want to, like this. So I just wanted to say, if we wanted to access individual elements, we could do it like this. So this is if we want to initialize the whole thing, and we would have to put 4 values in here because it's 4. But if we wanted to do them individually in a different way, we could. So it's sort of redundant. We could do either or of these, but if we want to do both, we can. It's not really going to hurt the program. These are going to be the values that are actually in the array at this point in the code afterwards. I'm just going to put some white space down here so I'm programming close to the middle of the screen like I usually do. Okay, So setting up our initial values, this is nice. See if there's any questions here. Someone was fiddling around with arrays of characters. Yes. We'll talk about that later. You may have noticed that things go weird. There's more subtleties involved. We'll get to it. Education. I should record an entire album of C code raps. Kevin's asking if I take any other courses besides COMP1511. Hasn't been 100% confirmed yet. Next year I may be taking a different course at some point in the year. But, it's all spoilers. I'm not going to say what it is yet. We'll get there if and when we get there. It depends. We haven't finalized all our allocations for next year yet. So we'll see how we go. Josh is asking if I changed this to anything other than 4, would this cause an error? Yeah. So we do have an issue here of me setting up this with this wonderful possibility of being able to change a number of players and then immediately writing 2 sections of code which don't allow that to change. So if we were going to do this differently and we said, okay, we're going to scan in, we're going to loop and scan in for the current scores of the players, then we could do this having this as the loop limit, and that would probably work a lot better. And then we would do something like this, where we say, look, just set them all to 0. I don't know how many there are, but set them all to 0. But for the moment, I wanted to show you a few different ways of initializing. Okay, so now we have our scores. One thing that we might want to do is we might want to loop through this array and print out the current player's scores. So let's write a loop that can do that. So I'm going to start using this standard programmer terminology, which is the int I equals 0. I is short for iterator, and iterator moves over the elements of the array. So I didn't say it last time. I used it as a counter previously because we didn't have an object we were iterating over the individual elements of, and that's what the I stands for. This is one of those cases where a single letter variable name is very, very much accepted in programming because the I equals 0 is it's like one of the most fundamental things that we'll see in looping programming. So we've got a while loop, and the while loop is going to go from player 0 up to player 3. So it's nice I've got these written out here. So I know that num players is my limit. So I will not reach the number in num players because the number in num players is not a valid element of the array. The array is 0, 1, 2, and 3. So 0, 1, 2, 3, and there's no element number 4. So I want to be strictly below that number 4. So I'm going to loop through, and as I loop through, for each player I'm going to print out some information. So printf player something has a certain number of points. Which player is going to be the iterator number, so it's going to be player 0 through to player 3. So I'm going to say I. So player I has a certain number of points. And to access the points, I'm going to access the scores at I. So first time this loops through, player 0 has 55 points, and then player 1 has 17 points, etc. So this should loop through the 4 and do that. Now, things that we were talking about on Tuesday that I would like to do. I think that in the overall running of this program, there's a very, very good chance that I'm going to want to print out the player scores more than once. If I'm going to want to print out the player scores more than once, I don't want to be copy-pasting this thing into multiple places in my code. Anything that I'm thinking about reusing more than once is a very, very good candidate for something that should be put into a function. So let's put this code into a function. First thing I'm going to do if I'm going to create a function is I'm going to declare it here. I think that a printout function that's just going to display stuff to the user is not going to need to give me back any information in the main. So I think it's a void function. I'm open to changing this if I start playing around with things and I think I need information back from that function. But my guess for the moment is it's a void function, so I'm going to start with it like that. I'm going to call it print players? It's not really print players, it's more print scores. And then I think, okay, if I have this function and I want to print out the scores, what information does this function need in order to be able to work? Because remember, what goes on inside curly braces stays inside curly braces. This function will not know this unless we give it to it. So I say, okay, you definitely need this array. If you need this array, I will give you this array. So I don't necessarily want to give it the same name because I don't want to confuse you. So we're going to make an array inside this. Actually, it's not really making the array inside. It's giving us access to this array. But it has to say, this is the array we're going to get. And we can say how big that array is going to be, like so. So now we take a copy of this and we put it down here. And we say, I always like to, with every function down here, say what it does. Because all these functions are going to be in a jumbled mess below the main. And so we won't have as much context for what they mean. So every function that I create, I like to have a comment. A function that prints out all the current scores given in player scores. So we assume that we get given an array, and it's an integer array that has num players length, and then we're going to loop through that array and print stuff out. So this code here that I've used that loops through and prints it out is actually going inside the function. So this function now, anytime we call it, it's able to print out the player scores. Pretty sure, yep, just double checking that everything matched up. So if I want to use said function, I use the name of the function here called print scores. Print scores, we know we can use it because we already knew what it was from up here. We need to provide print scores with an integer array of size num players. Good thing we have an integer array of size num players here. So what I can say is, I will give you an array of that size. So note, when I pass an array into a function, I'm passing it in by its name, just its name. If I started using the square brackets here to pass something in, I would be passing in an individual element of the array. So if I do this, what I am giving is the first element of the array, a single integer. I don't want a single integer. I want the whole array to go in, so the whole of scores, so I just use its name on its own. So little details like this are things that are going to catch us out at the beginning. So what we're getting here is a function that takes in an integer array, and then it does all this stuff, looping through and printing stuff out. I think we've written enough code now that we do want to test it. In fact, like, we can't really test it until we're printing. But what we can actually do is, now that we've got a function, makes things really easy. I can print scores multiple times. Oops. So I could print out the scores at this point in time when they're these numbers, and then after they've been set to different numbers, I can print them out again. And we can test this to make sure that that things are working. Mihir was saying, I've got a potential issue here that I'm trying to access scores, but scores doesn't exist inside this set of brackets. So the reason I named them differently is because I wanted you to think of them differently. This array, player scores, exists inside this set of curly brackets. So, did I say player scores? This array scores exists inside this set of curly brackets. It does not exist anywhere else. So this set of curly brackets here actually has a different name for it. Even though it's looking at the same array, I want you to be clear that the stuff that's inside the function is its own set of things, and the stuff that's inside this main function is its own set of things. Generally, what happens is anything that goes in as input to a function will just sort of be copied over, and it won't access the same thing. Arrays are a bit different actually, because you can actually get access to the same array by doing this. But let's see this running, and you'll see me using the print scores function twice here for these two different sets of scores. So we'll compile this, tab completing there. Oh, actually, you know what I'm going to do? I'm going to clear this so that you can see the text. Okay, DCC player scores, and my output file is going to be, I'm going to call it the same thing, player scores. Oh, there's a new line. I didn't notice there wasn't a space in between those. Okay, so I've now created, oh, I didn't actually go into my lecture 6 directory. I'll clean that up later. Actually, no, I'm not going to clean that up later. I'm going to clean that up now. I'll close this for now. And I'm going to move files, MV. I've got player scores, and I'm going to put a star here. So player scores star is going to match all the files in here that have the word player scores at the beginning and anything afterwards. So that should be all 3 of these files. I'm going to move them into the lecture 6 directory. ls there's nothing now in this directory, and I go to lecture 6, have a look in there. Now my player scores is in here. Just so that I've got my code file, I'm going to open tab completing, player scores. The AND means both windows will be active, and yeah, I've got this again. So I just was nearly being disorganized because I was working in the wrong directory, and so I fixed that, which is good. Okay, so we've compiled, now we can run this. Let's see what it'll tell us. Ew. Ew. Did anyone see that? Did anyone see the tricky little point where I didn't create the while loop correctly? Anyone remember how I would exit this loop now if I've accidentally made an infinite loop? All right. So a couple of people noticed it. So a couple of people were yelling out, "He's behind you!" there. The dastardly villain of me forgetting to put the I++ in, or did I forget, puts us into this infinite loop here, and everyone's saying Control-C. Good. Control-C is how we exit this. Control-C will tell me that I was in player scores at line 40 when this happened. So, player scores, line 40 says I was inside this function, and then I can see, okay, let's have a look at this loop and figure out why it went forever. I is less than num players, I is equal to 0, 0 is always less than num players, well, if num players is 4, as it is. Therefore, this loop will keep running forever. So what I forgot to put in here was an I++, which was going to increase I until it hits num players, and then we'll end that loop. Okay, so let's try that. Let's compile that again. I'm using my up. Oh, I shouldn't use my up and down arrow keys. Oh, I actually just got to the command there. We'll recompile this, and hopefully this time, now that we've compiled this and we've corrected that little error, and we run it, these loops are actually going to finish. Okay, so once through the loop, here is printing out these 4 scores, and then we changed all the scores, and then we're printing them out again, which means that this code here, we're now able to run it as Josh has caught me out. No, that was actually a genuine mistake. I actually just didn't write I++. Sometimes I just write loops, and I'd expect my computer to understand what I'm doing. But I thought that was really good, because I think it's actually good to remind everyone about the Control-C. Especially in your tutes and labs this week, I think a lot of people will potentially be doing that mistake that I made, or things like it. So it's good to see those. I'm going to justify every mistake I ever make as a learning experience. The trick now is this one little line allows us to take all of this and rerun it. And also, that I++ mistake that I made, it's not in two places now. It's only in one place, and now that I've fixed it, it's fixed for every time this is going to run. So I hope now what you're starting to see is the benefit of using something like a function. I've reduced the amount of code I have to write, and I've reduced the number of places I have to look for things if I need to fix an error. That I++ error was so good, I'm going to start doing that every time now, because I think that that has shown so much more about functions than if I'd just written correct code. So yeah, so you see multiple places being able to use it, only having to fix it in one place. It's like the best of all possible situations here. Okay, so now we have the ability to print stuff out. What I've also shown you here is the ability to loop through an array. So if we say I is less than the size of the array and it starts at 0, then I is going to, at each point in this loop, look at exactly one of the elements in the array. I might actually put a comment in here as well, is that we have seen I elements of the array. It's nice to actually kind of go through there and say, every time I'm looking through this loop, I know how many I've seen before. It's just nice to have those comments. It just reminds us of what we're doing. Okay, so we've got that there. And we can loop through and print out the values. So I think this is the same kind of code that we've been doing. Ningting's saying there is no return 0 in the main void and it is still working. Yes. So one interesting thing about C with the return 0 thing is if you don't give it a return, C is actually going to return 0 as it's going to return 0 on its own if we don't say it. If we explicitly say to return something else, then it will do that, but otherwise with the 0 it's just going to be like that. Okay, so let's write another function. So I want to say, for example, I want to look through the list of scores and I want to see who's winning at the moment. I'm going to write another function saying, what do I call it? I think I'm going to call it find winner. And that's also going to need the current scores. I'm actually going to call this one current scores in this function. So even though all of these are ending up pointing at the same array, I'm going to give them a name that makes sense for the function that they're in. This is going to need to give back some information, I think. So I think I want to know the index of the player that's currently winning when I do find winner. So I'm going to copy this, I'm going to paste it down here, and I'm going to put some comments in here about it. So find winner will loop through current scores and return the index of the current highest score. I'm going to say the current highest score. So even though I'm saying find winner here, I want to be explicit about what I'm determining as the winner. Because a different game might have the lowest score is the winner. I don't know if you ever play like Bridge or Hearts and stuff like that. I think lowest score is... Oh, not necessarily. Or Hearts maybe I think is lowest score. Yeah. Anyway, so for the moment I'm saying loop through and find the highest score. So what I'm trying to do here is go through all of the scores in the list and say which one of these is the highest. And I'm going to use a particular technique for this where I'm going to save who I think is the highest and then look at everyone in turn and say, are you higher than the person I think is the highest? If you are, now I think you're the highest. And then I keep going through to the end of the list. And so I check each player one in turn and check them against who I think is the highest. So in order to do that, I'm going to say, I'm going to store the highest. And for the moment, I don't know what that is. So I'm just going to leave that there and think about what I'm going to do. I might actually do this in comments first. Store the current highest, then loop through, and if we see anything higher, replace the current highest. So this is the highest score. I'm gonna do that because I want another variable that's also tracking the highest index, because I know that I'm going to want to give back the highest index. Okay. What are people saying? Dan's asking, are we required to know how to use the void thingy? We will want to know whether we're doing a void or a not void, because if I did this as not void, I would have to return something. So I'd have to say, what am I returning a number? Is it something? So since this is not returning any information, then I don't have to make it a type, which means I make it a void. This thing is returning some information, so I'm saying it's going to give back the index of the current highest score, so I'm going to make it an int. So I would learn the difference between an int and a void like that. Oh, are you talking about the main? Oh, Dan's wondering about the structure. Let me just continue this, and we'll stick around afterwards, Dan, and we'll talk about the difference between these. Because I do want to actually just get this function done. We've got 9 minutes left, which is enough time. But I want to show you this technique for finding the highest score. So if we want to loop through and find the highest score, then we could have the current highest score. So what I'm going to do is I'm going to make an assumption about my scores for the moment. I'm going to assume that there is at least one player in the game. So assuming that there's at least one player in the game, I'm assuming that player 0 exists. So what I'm going to say is current scores 0 is the highest score, and the highest index is that player. So these two are going to match, where the highest index 0 is going to match up with that current score. In fact, I will show you in a second how I may not even need one of these. Actually, you know what I'm going to do? I'm going to do that from the beginning. I don't need to store the current highest score. I may only need to store the current highest index. But let's go through this loop and have a look. So, same thing as before. We're going to loop through the array of scores. So we're going to have an I, and if we want to, we can start this at 0. But I'll show you in a second that we might not even need to do that. So I'm going to piece this together out of many possibilities of what we can do. I know that we're going to loop until before num players. This is the generic loop that will look at every element in the array. And then when I'm looking at a particular element in the array, I'm going to say, is the score that I'm looking at higher or lower than what I think is the current highest? So I'm saying, is it higher or lower? I'm using an if statement. Basically, anytime you ask a question, chances are it's an if statement. So is the current scores I, so this is me looking through them all one in turn, is that greater than the current highest score? So I'm going to put a comment in here for what happened in this if statement. So score is higher than previous highest. Replace previous highest. Okay, so if I'm going to replace this, what I'm saying is that the current value that I think is the highest in the list, because this one's higher than this one has no right to still be the highest score. So the value that was in I, in current scores I, replaces it. So I'm going to say that the new highest score is equal to current scores I, and the highest index is now equal to I. You may note that this value here, highest score, I never actually need it because I have the highest index, which means I have access to this. So what I'm going to do is actually take this away because I don't need it. So what I'm saying is I have the highest index, which means if I want the highest score, I just read the value that's in the highest index. So current scores, highest index. So now what I'm adding to what we had before was the ability to access an element of the array using a variable index. So we start at 0 and we say, is what's in the highest index less than what's in the current scores? So is the current one we're looking at, the I, higher than our previous highest? If it's higher than our previous highest, we don't need highest score anymore. Then we say this is the highest index. And so what we're going to do is we're going to go through the list one at a time, and we're going to say, is this one higher? If it's higher, it replaces it. Is this one higher? If it's higher, it replaces it. Is this one higher? So basically what we're going to do is go through the list, and we're eventually going to find the highest number in the list. Because whichever one in the list is higher than all the others is the one that ends up being the index that stays there. So at the end of this, highest index is now the index that contained, actually I might just put this on its own line, is now the index that contained the highest value. Okay, so now we know that that index is that. This function needs to give that index back as an integer, which is fine because highest index is an integer. So I can return highest index. Okay. So to be clear on what this is doing, oh, did I leave out the I++ again? Okay, so what this is going to do now is it's going to loop through the list, and it's always going to check the element it's looking at in the list against this other thing that it thinks is the highest that it's seen so far. Interesting thing that we can also do is if we've set the first highest index is equal to 0, we don't actually need to check 0 against itself. Because if current scores I is 0 and current scores highest is 0, which will be the first time we go through, there's no need to check them against each other. So I can actually start this at 1. So there's lots of little things that I'm showing here about how we can have like subtleties in code to change things. Because if I already think that 0 was the highest I'd seen so far, then I don't need to check it. I can check it against the second one. So check the first against the second and then continue onwards. Okay, so find winner is going to give me back an index. So I can then run this now as a function, and I can say int winner index is equal to find winner. Find winner is going to need the array to be able to run, similarly to how print needed the array. So we have our scores there, and then we can print out something along the lines of the current leader is player something with a certain number of points. And we're going to have the player index, which is the winner index. This idea in the back of my head of calling that Windex then, I thought that would have been funny. And their score is scores winner index. Okay, I've gone a bit over there, so I might actually just drop this printf a little. Wonder if I'm going to make this, yeah, I'm going to make this super complete, super correct like that. So I'm doing the printf as if it's a set of curly, the same way I do a set of curly brackets. one thing per line and indexed in like indented in like this. Okay, let's try running this. So winner index, find winner, is going to jump to here, and it's going to go, let's just assume that the first is the highest from now on, and loop through everything else in the list and try to figure out which one is the highest. There's a lot of assumptions here. This list is A, assuming that there is an individual element in it. It is also assuming, oh, actually no, it's not assuming, I was about to say it's assuming that there are other elements in it as well, but not necessarily. If there's only one element, this while loop will never run and highest index will be 0. But it is assuming there's at least one in here, because otherwise we're going to return 0 for an empty array, and then you still can't access anything in it. Okay, so let's run this and see what kind of score it gives out. Hopefully it gives us the 94, because it's gone through and checked all of these against the highest. So we're going to compile that and run it. All right, current leader is player 3 with 94 points. The I++, people are laughing about there. Okay, so that's as much as I've got time for here. But I hope what we've seen today is a couple of things. So I didn't talk about another syntax I was going to talk about. Maybe I'll talk about that next week. Okay, so we've got the score tracker. We don't have all of the stuff in the score tracker, but what I wanted to talk about is what we talked about today. Is right. So a lot of the theory of the computer, how the processor works, and how it's and how memory works, and things like that, and how they all fit together, and then arrays. And what we've done here with this program is we've shown a lot of things: how to declare an array with specific values, how to access individual variables in the array, how to loop through an array and do something with every element. So we can loop through the array and access individual elements of the array. And then we did one more advanced function, which is, can we loop through the array, testing things about the array, and can we store information outside the loop that we're going to reuse? So there's a lot of little things that we've done here. I will wrap up the lecture there now. Sorry, I've gone a couple of minutes over time, and I'll just go into break mode and I'll be right back. Stick around if you have any questions you want to ask or anything that you want more details on. See you later. All right, I'm back. Do we have any questions? Also, I have a question for everyone there. Are there any blinks in the uh in the uh in the lecture right now? Because Blackpink is releasing a new album today, and I think they might be live streaming right now about it. So I would be very, very. I'm actually very, very surprised that you're here instead of there, because if I had a choice, but I mean it's much harder for the lecturer to just go, look, I need to ditch the lecture because Blackpink are live streaming their new album and it's very important. But anyway, both me and them will be recorded, so I assume there's a bunch of links who are not here right now, obviously, but then there's some who are. So thank you for choosing me over Blackpink. That makes me feel very, very important in the world. If I have been chosen over the people who get like 1 billion views on their stuff. Okay, so first question that came up was from Dan. Um, do you mind explaining the format and what happened in the code again? Is there a particular part of the code that you want to look at? Is it the structure of how the functions are working? Or is it something else? Akira-chan was here for chicken. By the way, let me just get out of the way. There she is. She's just basically been sitting behind me the whole time because she knows that, like, basically if she just sits behind my butt, she gets a lot of free human warmth. So you'll find parts of the lecture where I'm just like, why is he leaning forward the whole time? He's not sitting back in his chair at all. It's because I don't want to crush her. So she's just back here this whole time. Okay, so Dan, let's dive into details. Do you have anything in particular that Savesh is asking if you can rename her chicken? Yes, she can have a DJ chicken, and when it's DJ chicken, it's like CHKN, which is very cool. Anyway, so Dan, you were wondering about the format. Is this the layout of how the functions are put up here and then put back down here and things like that? Right, function and void. Okay, so remember that every function that I create, and we'll just look at the simplest version of it, is just the declaration of the function, has a certain structure. So the type of the function is what the function outputs. So the information that comes from the function back into the main. I'm going to say it like that. It's not entirely true what I'm saying because some functions call other functions. We'll go into that later. But the function where it is run in the main can be used as the type that it was. So if it's a void, it can't be used as anything. It just runs and then continues. However, this one here says take the function and use the function as a value for this variable. So if the function is going to be used as a value for the variable, that function has to be the same type as the variable. So I'm saying the winner index is an integer. Set that integer to whatever the result of find winner is. Find winner says I will be an integer type, which means that when find winner runs, it will return an integer type value. So highest index here is an integer type value. I've said I will return this integer type value. It's going to be one of the indexes, but that's not super important. The only thing that we've said is it is an integer. Therefore, when find winner runs and finishes, it will finish on this line return. Even if I actually, if I write a whole bunch of other code afterwards, none of this code will run because the return will say this function's over. It is returning now. Obviously that's not code, but if it was, we can actually use that sometimes to force a function to return early if it finds some other situation. It's a bit fiddly though. What I usually do is prefer the return to be at the end so that you can read it top to bottom. But anyway, the important point is this will return this value, which is an integer value that was started at 0 but could have been changed to any of the I values depending on the conditions. So depending on whether it found a higher value in the array, it will change what the highest index is. And then it returns highest index, which means that this running of this function, this point, whenever we run a function, we jump out of our main and we jump into the function's code. We jump into the function's code, we hit this return, then we jump back into the main. But when we jump back into the main, this no longer is the function find winner. It's the value that find winner turned into when it returned. And that's going to be whatever the value of highest index was at this point at the end. So find winner now is an integer, and it's an integer that can be placed into a variable. So it's an integer value that can be stored in this variable winner index that is then used here. So the difference between these is the void is never used. So we can't take this and say int print value equals this, because it has no value. It is void. Void says I don't give you anything back, so you can't assign the result of this function to anything. All this function does is it performs a purpose and ends. As opposed to this function here, which performs a purpose, gathers some information, packages it up, and gives it back. And when it gives it back, it can be stored like this in an integer. Hopefully that gives you a bit more information about how those work. Ningting's asking about the return 0 at the end of the main. You won't lose points in the exam or in the assignments if you don't have return 0 at the end of your main. You'll notice that there's a lot of possible return 0 or not in what we do, and so it's not mandatory at all. That's why I wanted to show it happening and not happening, because it's not important enough that it has to happen. Okay, Peter's also asking, in terms of declaring the function find winner, how does current score help calculate the score? So here, declaring find winner, oh, Nasa's got a question. I'll get to your question in a second. Peter is saying, how does current scores help calculate the score? A bit confused about the structure of declaring functions as well. So, when we have a function like this, this is what the function gives back. This is what the main gives to the function. So the function is going to need certain information in order to work. So this is me saying that the function needs some input. So remember last time, let me just go to lecture 5. Function demo, that's it. Last time we had really simple functions where we were giving 2 integers to this and it was adding them together. So 2 integers and adding them together meant that when we called the function add, we were giving 2 variables. This one would copy the 3 in there, this one would copy the 7 in there, and then add would add the 2 of them together. So that's the basic function, where it's just taking 2 variables and putting them in. It's actually not that much different with an array, where I'm saying the array inside find winner is going to be an integer array of this size, and I'm going to name it current scores inside find winner. This in the add function was going to name the first one A and the second one B inside these curly brackets. So we've got this array in here, and we're saying give me an array that's of this size and I will use it inside here. So the same way that every function has some input parameters that go into it, and then it has an output type that it creates afterwards. So the things that it gets are in the brackets, and it can have more than one thing separated by commas, but this is just one thing, although it's kind of 4 things because it's a collection there. So this, we will require an array anytime we call these functions. And it just so happens we have this array of the same type. It's not the same name because it's not necessarily exactly the same array, because inside the curly brackets it's its own thing. Arrays are weird like that though, because you are actually accessing this array from inside the function, but that's a subtlety we'll get to later. So what we're getting here is that we've created this array that's the same format as these, so we can pass this array into each of these functions. We made these functions specifically so that they would work on this same array. Let's see if I've got any more questions here. NASA's asking, sorry, I still don't get what's the purpose of void if it doesn't return anything. So note that print scores does not return any information, yet when we run print scores, something happens. Yeah? So every time we ran print scores, we got to see this information as a human. So even if it doesn't return anything to the main, that doesn't make it worthless. It's still pretty useful for us to see what the scores are at any point in time. So this is doing something for the player, but it's not doing something for the program. But it's serving the program's purpose, because the program's purpose might sometimes be to display what the current scores are. So if this game was continuing and the scores were constantly changing, so every turn the scores change, and we want to know what's happening, we would say, okay, these are the current scores. We can also print out who's currently in the lead. So we could have something where this is looping turn by turn, people are getting different scores, and we're saying, okay, this is the current state of the game, and this is who's currently in the lead. And so this print scores thing, while it has nothing to give back to the main, it still might be vitally important to the program. Dan's asking, is commenting on my code important in the exams? Not super important. It depends on how readable your code is to yourself, with or without comments, and how important that is. Anytime an exam question, basically what we're going to do is we run all the exam questions through auto testing and our own auto marking system. If you get full marks or 0 marks, actually no, only full, if you get full marks in all of our tests, then we don't need to look at it. So we think this person has passed everything, and we've thrown a few curveballs in there to really test their code. It's different from the auto tests that you get. If you get full marks in that, we don't look at your code. If you get anything else than that, then we're going to look at your code and try to figure out how much you've been able to do. So comments may help, because they may help the marker read what you're doing. It depends if you assume the marker is so good at C that they don't need comments to decipher what you're doing, or you think your C code is so clear that you didn't necessarily need that. That's the kind of advice about comments in the exam. You don't need them though. Brenda's asking, what are the things inside the square brackets? So in different places where we use the square brackets, the inside the square brackets is nearly always going to be a number. There's two ways that's going to be used. If you see a type, like the type name integer, or other types that we might see, like double, for example, before the declaration of the array, this is a creation of an array. When we're creating the array, this is how big the array is going to be. After the array has been created and we're just using it, so you can tell we're using it because we're not saying what type it is, so we're not making a new one, we're just using it by its name. Inside the square brackets tells us which element we're accessing. So the elements in a 4-number array like this is index 0, 1, 2, and 3. So it always starts at 0 and counts upwards. So this is me going 0, 1, 2, and 3 and changing the values. So if I say scores 0, this is me saying there's an array of scores, and I'm looking at the first element of that array, scores 0. And once I've used the square brackets, I treat this thing here like just any other integer. So it's not always an integer. You can have an array of different types, but this one happens to be an integer array. So this is the first integer in the array, and we can do anything that we could do with a normal integer. So because it's an integer that holds a number, I can assign a different number to it. And that's what I've done for these 4 here. Dongyi Lin is asking why scores numPlayer is the same as player scores numPlayer. You haven't given player scores numPlayer any numbers yet. So this is how functions work. Simple demo here of the functions is, I have an integer a and b. Integer a and b do not exist, right? They're not here in the main anywhere, but I'm saying there's an integer a and an integer b. When I call the function, I need to give it 2 integers. So I give it the first integer that I created there and the second integer that I created. So what happens is the value 3 goes in here as the first, and the value 7 goes in here as the second, which means A, when this runs this time, A will be equal to 3 and B will be equal to 7, which means that if A is 3 and B is 7 here, result is 10. And so then we would give back a result of 10 when we finish running this. So the same kind of thing, player scores and current scores, these two variables that were created when these functions run, they will require some information to be created. And so the information that gets put in these in the main as this runs is we've got this array called scores. This array of scores gets put in here, which means that when print scores runs this first time, print scores here, it requires this array, and it's called player scores, is going to be the same as this. So it's going to be these 4 values, because that's what scores was when it was given to print scores. Those are the ones that are going to print it out. And you can see here, those are the values that get printed out. All Night is asking, where did current scores come from? Why not player scores? The reason why I named these differently is basically so that you would ask that question. Player scores exists only inside this function. Current scores exists only inside this function. What I'm showing you is that when a function runs, it creates these variables that are its inputs, and it creates them from whatever information it's given when the function is called. So these two both get scores, but you'll note that scores is different from this one than it is here, because scores has had its values changed in here. But each time this runs, it creates a new player scores, in a sense, with whatever was in it. It's a little bit weird and different, but that's generally how functions work. It's a little bit different with arrays, but it's okay to still think of it like that. So this array called player scores is whatever this thing was given. And this one gets given something, same, but it calls it current scores. And so within their own code, they've got their own name for whatever information they were given. So I named them differently just so that you would see that these were not linked to each other. The only reason that these two feel like they're linked to each other is I happen to be giving them the same array when they run. But I can do something else. I can do scores team 2. And so there's now 2 teams. Let's say team 2. Team 2 does much worse, and they're all on 0. So I could say print scores of one of the teams and then print out the scores of the other team. So this function now is running twice, but each time it runs, it's running with a different player scores. So it creates the player scores here every time it runs. So the first time it runs with this array, and the second time it runs with this array. So every time we run a function, we give it input, and the input can be different every time. The only thing that has to match is the input must match the format. So it must be an integer array with this number of players in it. So the functions are able to work in many different ways like that. Okay. Hopefully that answers the question about what current scores and player scores are. They're created as the function is called. So next is asking, so void can do something for the human to understand, just not return to the computer. Yeah, so the information may not go back to the computer, but it still might be useful. And as we get deeper into these, we'll see we can use void functions for more than just communicating with the human. There's lots of little things that void functions can do. Peter's asking if they're similar arrays but different name. Yes. So similar in that they are an integer array with a certain number of elements in it, but they are created only for the purpose of the function itself. Having said that, these actually will link us back to these arrays, so we can actually access them like that. But in general, when we do functions, the whatever we pass in here is going to be recreated inside the array, inside the function. So JD's asking, why does find winner have current scores in its brackets, but when you use it, you put find winner scores? So hopefully I've already answered that question, which is that current scores is an array that only exists inside the function itself. So I'm saying that you will give me an array and I will name it current scores in here when I'm using it. Then when I call the function here, I need to give it an array that's of the correct type. The function itself will give it its own name inside. So it won't keep the name that I gave it. It'll get given a new name inside the function for the function to use. JD is saying, how do I understand which array it takes? Like, what I'm thinking right now is there are two sets of scores. Which set does it operate on? Okay, so if there are these two sets of scores, which one it operates on is which one it was given. So I could run find winner on scores, and then it would run on these. If I do find winner on scores team 2, it will then act on this array rather than this array. So the input that we give to a function changes which piece of information the function is going to act on. So this one's pretty boring because they're all 0. But this says that when find winner runs this time, it gets given this array, which has, I think, these values in it by this point, and then it will use that as its current scores. So its current scores will be the array with these values in it, and then it will be able to spit out an index saying which one of these it thinks is the highest. So every time, I think we need to have a quick look through the order of how things happen. So when we run our program, it goes from top to bottom, and it does each line one at a time. So this one sets up scores to be these values, and we set up scores team 2, which is just an example thing. I'll probably remove that. And then we go print scores with scores. So what's going to happen when I do this is the program control goes line by line, but when it gets here, it jumps down to here and says, okay, I'm going to run the code that's in here. In order to run the code that's in here, I need to create an array called player scores. And how do we know what this player scores is it's the thing in the brackets. So here, and the thing in the brackets will become player scores. So whatever was in the brackets here will become whatever's in the brackets here. So scores here with all of this means that what I call player scores in here will be accessing these numbers. So when I say player scores I, so I start at player scores I, so player scores 0 is going to go to whatever I was given, scores, and go, okay, scores 0 was 50. So that's the number that I have first. Player 0 has 50. And then it goes to number 1, and it says player scores. So what was in the array player scores is the same as whatever was in the array scores at that point in time when it was run. And note that when I do it again down here, it goes to these numbers because everything is done in time, one step after the other. So this one runs player scores over this. This one runs player scores, but this time it uses this array, the team 2 array, because this is the thing that it's been given. So the name that I give it in here is the variable from my program that gets passed into the array. So it's like when the array runs, it gets given information, it runs on that information, and then it may give some information back. You can actually run functions without giving any input, even. So there are some functions that I could declare that have no input at all, but they run something. The more we work with these, the more you'll see different options we can use for these. So print scores will run using this first array, and then print scores will run after this one finishes. Then print scores will run using the information from this array. Then down here, print scores will run also using the information from this array, but because these steps have happened in between, the values are going to be these ones rather than those ones, because these values don't exist anymore. They've been overwritten by these. Likewise, when find winner runs, the array that it uses inside is going to be whichever array it was given when it ran. So every time your function runs, it gets given information from other parts of the program, and the information is exactly what's written here when it runs. So whatever is inside the brackets here is what gets made into these variables in here. So simplest possible way of looking at this is I'm adding two numbers together. When I call the function, so when I say the function will run now, I put in two variables. So the first variable here happens to have the value 3 at this point, which means that this variable that's created here starts off with the value 3. And then the 7 goes in here as the second value, which means that B, when it's created this time, when it runs, has the value 7. So it takes the values from whatever variables it was given when it ran. Hopefully that's giving people more information about how these functions are running. How are we doing at the moment, everyone, based on this like run through that I've done here? Are people starting to pick up what's going on? Let me know. Dan's asking if we're going to do more functions later. Yes, we are. We're going to see them, both functions and arrays, in our tutes and labs next week. We're going to continue using functions for the whole of 1511. So you're going to get a lot more practice with these. So we've seen the simplest level of using them here. We started to make them a little bit more complicated here by passing arrays into them. Next week, I think we will try actually using functions within functions as well, which is some cool stuff. Dan, I'm not sure. There is a textbook which you could look at, which would show things a different way. You can also wait for the tutorial next week and see if your tutor is going to teach it a different way than I am, and then you may see other perspectives on it. So there's a couple of different things you can do there. Obviously, the other option is you can just hit Google and see what other people say about what are the nice ways to learn functions in C. So hopefully, if you do any of those things, you'll see it taught from a different perspective from mine. And usually, when you see something taught from multiple different perspectives, you get a decent idea of what the subtleties are, because there could be some things in the way I'm presenting it that are not clicking with you in a specific way. But if someone else presents exactly the same material just from a different perspective, it might click. So it's often good to see more than one teacher's look at things. As much as I would love you to learn only from me, I don't really like that, actually. I think it's better that you learn from multiple people. I think it's very good to learn from multiple people. So I think there's always other ways to look things up. The textbook is going to have a whole chapter on these. The tutes and labs will spend an hour or two on these as well. And the other thing is we're going to keep using these. But I do fully understand if you want to get a better knowledge of this before I continue. So that's what I'd suggest for other resources. Um, I think there's probably going to be some YouTube channels where people will teach C functions, and they may have recorded material that goes for longer than what I have spent on it, so maybe that will help as well. Who knows? Okay, I think I should wrap it up there. Hopefully, everyone has gotten a little bit more about both functions and arrays today. Um, and we'll see how we go next week once you do your tutorials and things, whether this stuff starts to settle in better, and you start to really get the idea about how it's going. Another thing I could say is keep playing around with them, because there's more stuff you could do with this player scores demo. So I was doing other possible things. You could follow some stuff from the lecture slides as well for adding up the total of everyone's scores, or making a new function that's like find winner, but instead of find winner, it's find loser or something like that. Yeah. So before I head off, I think Alfred has one last question. Just to confirm, the quiz can be attended as much as we want. So we're talking about the weekly test. We have a timer on it for 1 hour. That's for your own feedback. At the end of the hour, you can assess how you're going. It's really about you getting to learn where you're up to. You can keep doing it. Yeah. So you can keep doing it all week if you want to, until it's perfect, until you've learned everything you need to know. I'm never going to tell someone that they shouldn't do more learning, because it can be really useful. So yeah, the time limit is there for you to get some feedback. It's not a limit that I need for anything. I don't mind if you keep working on things, or you go back and you look things up and you really nut out exactly how you want to do things. So yeah, there's no real limitation on submission. The 1 hour limitation is, this is a good amount of time for you to test how much you know. Alrighty, I'm going to wrap it up there. Thank you all, and I'll see you on Tuesday.